In this video, we will learn how to solve a constraint optimization problem with three variables. The question is, a firm uses three inputs, K, L, and T, to produce output according to a production function. That is, production is a function of these three inputs, that is equal to K raised power 1 upon 3 times L raised power 1 upon 3 times T raised power 1 upon 3. The cost of input K is $1 per unit, and cost of L is $2 per unit, and the cost of T is $4 per unit. The firm wants to make 10 units of output at minimal cost. We have to find out the optimal units of each input required and the minimum total cost for producing these 10 units. Okay, so what we are being given, and let's write it here. We have this production function, okay, and we can write it as, let us say, Q is equal to, that is, f of K L T, which is being equal to K raised power 1 upon 3 times L raised power 1 upon 3 times T raised power 1 upon 3. Also, we are being told that price of capital, that is PK, is $1 per unit, and price of labor, here L, let us suppose it is labor, it is being told it is $2 per unit, $2 per unit, and price of another input, that is T, it is being given us as $4 per unit. Okay, since we have to find out the minimal cost, that means this will be a cost minimization problem. For that, what we need to do first, let us find out the cost function. What will be the cost function? That is, C will be equal to price of capital times units of capital plus price of labor times units of labor plus price of T, which is another input, times units of T. Okay, that means C will be equal to, so PK is 1, so we can write here only K, plus PL is 2, so we write 2L, and since PT is 4, we can write plus 4T. Now, what is the endeavor of this firm? It wants to minimize cost, that is C, which is equal to K plus 2L plus 4T. Okay, so the problem will be to minimize this cost function subject to the production constraint. What is the production constraint? That means in place of Q, since we are supposed to produce 10 units, that means our production constraint will be equal to K raised power 1 upon 3 times L raised power 1 upon 3 times T raised power 1 upon 3 should be equal to 10 units of output that is to be produced. Okay, so this is a cost minimization problem. And how do we solve this? We solve it, forming the Lagrange function first. Lagrange function. For that, how do we construct the Lagrange functions? Very simple. First, we rewrite this, production constraint, and let us set it equal to 0, which implies 10 minus K raised power 1 upon 3 times L raised power 1 upon 3 times T raised power 1 upon 3 is equal to 0. After that, what we do to this production constraint, we multiply both sides by lambda. Okay, then we form the Lagrange function like this. So let us denote, L denotes the Lagrange. Okay, and this capital L denotes the Lagrange, which is equal to, we write this objective function first. Lagrange function is formed by adding objective function with the resulting production constraint that we formed here. So our Lagrange function will be K plus 2L plus 4T. To this we add this resulting constraint that we formed, which is equal to lambda times 10 minus K to the power 1 upon 3 times L raised power 1 upon 3 times T raised power 1 upon 3. Okay, this is our Lagrange function. Now, to find out the optimal values of capital, labor and T used in this production process to minimize cost. What will we do? We partially differentiate this Lagrange function with respect to K, L and T, set them equal to 0 simultaneously and then solve them. Okay, so let us denote L subscript K, that is the partial derivative of this Lagrange function with respect to K. So derivative of K will be 1. Okay, since we are taking partials, no K is involved here, its derivative is 0. For T its derivative is 0 because we are taking partials with respect to K. Here in this equation we have lambda times K raised power this stuff. Okay, so what will be the derivative here? It will be equal to minus lambda times, what is the derivative of K raised power 1 upon 3? K raised power 1 upon 3, its derivative is 1 upon 3 times K raised power 1 upon 3 minus 1 by power function rule. If we have x raised power n, its derivative is n x raised power n minus 1. Okay, so I can write it as minus lambda, since derivative of 10 is 0, so we are partially differentiating this very stuff here. We got minus lambda times 1 upon 3, 1 upon 3, then we have K raised power 1 upon 3 minus 1, and these two terms will remain same because we are taking partials with respect to K here. So we have L raised power 1 upon 3 times T raised power 1 upon 3. Okay, and we set it equal to 0. Let me solve it here because I don't have the space here. So let us rewrite this. I can write this function as 1 is equal to lambda times 1 upon 3 K raised power 1 upon 3. If I transpose, or let me rewrite it here, K raised power minus 1, I can write in place of this term, I can break it into K raised power 1 upon 3 times K raised power minus 1. Then we have L raised power 1 upon 3, then T raised power 1 upon 3. Okay, now I can rewrite it as 1 is equal to lambda upon 3 K raised power 1 upon 3. Let us transpose this to denominator, so it will become K raised power plus 1. Okay, so it will become K only here, this term, when I transpose it to the denominator. Then we have L raised power 1 upon 3 times T raised power 1 upon 3. So what happens here? If I multiply both sides by K, so or transpose this K here, it will get multiplied with this one. So we will get K is equal to lambda upon 3 K raised power 1 upon 3, L raised power 1 upon 3, T raised power 1 upon 3. Okay, when I solve this stuff, I will get this stuff. So K will be equal to, K is equal to lambda upon 3, K raised power 1 upon 3, L raised power 1 upon 3 times T raised power 1 upon 3. Okay, and let me rub this out now. Symmetrically, we need to find out the partial derivative with respect to L. So L subscript L means the partial derivative of this function with respect to L. What will happen here? Derivative of L will be 1, so we are left with 2. Then we have lambda into minus is minus lambda. And here by the same logic, we have to differentiate with respect to L raised power 1 upon 3. So we will get 1 upon 3. K raised power 1 upon 3 will remain same. L raised power 1 upon 3 will become 1 upon 3 minus 1. T raised power 1 upon 3. Okay, and we set it equal to 0. When we solve this again, what will we get? Like I have explained it in this process. So this 3 will go here. So we will get 3K. Sorry. When we solve this, it will become 2 is equal to lambda upon 3 K raised power 1 upon 3 L raised power 1 upon 3 divided by L T raised power 1 upon 3, which implies 2L will be equal to lambda upon 3 K raised power 1 upon 3 L raised power 1 upon 3 T raised power 1 upon 3. Okay, let us say this is equation first, this is equation second. Similarly, we need to find out the partial derivative with respect to L subscript T. That means this time we need to differentiate partially with respect to T. The derivative of T is 1 in this 4T, so we are left with 4. Okay, 4 minus lambda, and here the derivative of T raised power 1 upon 3, so this will become coefficient 1 upon 3. Then we have k raised power 1 upon 3, L raised power 1 upon 3, T raised power 1 upon 3 minus 1. Again, what will we get when we solve this by this process? So this will go here, so we will get 3. Okay, so we will get 3t, you can see it, 3t, rather 4t here. Okay, so let me solve this to make sense. So L, when we set it equal to 0, let me see what is happening here. So 4 is equal to lambda upon 3 k to the power 1 upon 3 L to the power 1 upon 3 t raised power 1 upon 3 upon t. So we will get 4, and let me write it here now. Okay, or let's write it here. So we have dividing both sides by t, we will get 4t is equal to lambda upon 3 k raised power 1 upon 3 L raised power 1 upon 3 and t raised power 1 upon 3. Let us say this is equation 3rd. Here you can see in the first equation the RHS of the equation first, the RHS of equation second, the RHS of equation third are same. Okay, if RHS of the three equations are same, we can equate LHS. Okay, simple thing. We are saying if x is equal to 20, y is equal to 20, z is equal to 20, so we can say that x is equal to y is equal to z. Here we have the same RHS like this. We have this stuff here, and this stuff here, which are equal to each other. So we can equate these things. Okay, since RHS are same, we can equate LHS. That means k, here we have k is equal to 2L, which is equal to 40. Okay, now if k is equal to 2L, can I write it as L is equal to k upon 2? And if k is equal to 40, can I write t is equal to k upon 4? I can write it easily. So what will we do then? So we have the given production constraint. Let us solve this first. Okay, let us we can write this production from this. Okay, I'm just trying to show it how do we solve. So I can write it as k into L into t whole raised power 1 upon 3 is equal to 10. Or I can write k times L times t is equal to, transposing this, it will become 10 cube, or k times L times t is equal to 10 tens are 100, tens are 1000. So we will get here 1000, k times L times t. Then what will we do? We simply plug the value of k, L and t in this equation. Okay, plugging and the value of k, L and t in this equation, what will we get? So we have k as it is. The value of L is equal to k upon 2, and the value of t is k upon 4, and we equated with this 1000. 10 tens are 100, tens are 1000. Okay, pretty nice. So here we will get k into k into k, which is equal to k cube. So k cube will be equal to, so 2 4s are 8, tens are 8000 here, 8000, or k will be equal to cube root of 8000. Okay, since this is a perfect cube, so it's the value of k will be equal to 20 into 20 into 20, 2 to the 4 to the 8. So we will get so we have 20. Let us see if 8000 is equal to 20 into 20 into 20. So we have 2 to the 4 to the 8, then 3 zeros. Okay, so the value of k will be equal to 20. That means we require 20 units of k to minimize cost. And how many units of L? Simply what we need to do, L is equal to k upon 2. So L will be equal to, the value of k is 20 upon 2, which comes out to be 10. And what are the values of t required? So t will be equal to, the value of k we got 20, 20 upon 4, which comes out to be 5. Okay, so the thing is we need 10 units of labor, 20 units of capital, let me write it here, capital, and T, that is 5 units of T to minimize cost. And what will be the total cost then? So total cost will be equal to, simply plug the value of K, L and T into this cost function. So K is 20 plus 2, L we got is 10 plus 4 into 5, that is equal to 20. 20 plus 20 is 40. Let me see if I, so this is 20, 2 tens are 20. 20 plus 20 is 40. 40 plus 20 is 60. That means total cost will be equal to 60. Okay, I hope I make myself clear in this video. Thank you.